Hello everyone, Ron again, feeling extremely calm today for some reason. Today we're going to talk about phase and phase cancellation for the purpose of talking about mono compatibility in the upcoming videos. I'm not sure how many more there will be, maybe just one, maybe two, but it's kind of a lot to break down. So here we go. So you look at this right here is an oscilloscope. And what it does is it shows you the shape of a waveform. As we discussed previously, every sound has a waveform, and you can use those different waveforms to make different sounds, especially in synthesis. But a pure sine wave will only occur in synthesis because it doesn't occur anywhere in nature. For that reason, everything else has a fundamental frequency and it has harmonics above it. But if you look here, I'll play a sine wave. This is the shape that a sine wave takes, and as you can see, it looks exactly how it would in like a textbook. So it has a high point and it has a low point, and that high point is called a peak and that low point is called a trough, which is a word that I have just been pronouncing wrong this entire time in my head because I thought it was like trough. So for sound to occur, a sound wave cycles over and over again, as you can see here. A typical sine wave cycles from 0 to 1 and then back to 0, and then from 0 to -1 and then back to 0 again. The position of that waveform at a given time is called phase. For example, when the sine wave is at 0, it moves to 1, that is a phase shift. Every waveform has a shape. The term phase represents where the sound would be along the shape of that waveform at a given time. The highest point is called the peak, the lowest is called the trough. Therefore, when the typical sine wave reaches 1 from 0, it is at its peak phase. So each time when this sine wave is at the top, for the sake of argument, we're going to say that that's 1. And each time when it is at the bottom, that is -1. Now, if you were to invert the phase of the sine wave, right here, to demonstrate this, I have two sine waves. Well, actually, it's one that's feeding into a second channel, and then they're both summed together in channel 3. Channel 4 is my voice, so that's pretty cool. If I freeze the wave candy, you can see this in action, actually. So it's like it took a picture of the waveform. And here you have 1, 0, -1, 0, and it repeats like that. It oscillates, if you will. So when you invert the phase of a signal, that means to reverse its polarity. And polarity, you could think of it as kind of which direction it moves in first, in a way. Visually, that would mean it would turn upside down. So if this sine wave, if it had gone down, like let's say for the sake of argument, it went down first, and then it went up, and then it went down. If I reversed the polarity, it would go up, and then it would go down, and then it would go up. So visually, that's what an inversion means. The waveform is just reversed. It's turned upside down. Now I'm going to demonstrate here. If you combine the two sine waves, because I can unfreeze this, right? And I can just show you that. Turn one of them off, reverse the polarity. It turns upside down, even though it's moving too fast to be seen. You can sort of see it. You see that little flip as I click. In any case, that's not the point. The point is this. And here's actually, before I get into that, here's another point to make. You have what's called amplitude, which electrically is the amount of power that's going to whatever device is acting like a speaker for playback. But in terms of math, is just, you could essentially think of it as how loud the sound is going to be. It relates to gain, and I'm not going to be too technical about it. But an example of amplitude is here. I turned off the second copy of the sound, and when I turn the second one back on, you can see from this that the amplitude increases. You could think of that as how far away it goes from zero. And as that translates to what we see, that means that the signal is louder. So if I go here, there's a reverse polarity switch. As I discussed earlier, there's 1 feeding into 2 and into 3. So that 2 is a copy of 1, but it doesn't feed back. It just feeds into 3 itself. In other words, 1 plus 2 equals 3. But in seriousness, you can see here that 3 is it has a sound. So a sound is still being made. If I reverse the polarity, watch here, 3 will disappear. Now, why is that? And also you can see, based on the oscilloscope, that there is no waveform. So that is what phase cancellation means. If I make the polarity normal again, it's going to come back. If I turn off 2, it decreases. If I turn 2 on, it increases. If I reverse 2, it disappears. Why? Because when you invert the signal, the trough is going to meet the peak if the signals are exactly the same. And if you think of the trough as being -1 because it's the low point, and you think of the peak as being +1 because it's the highest point, they sum together and they become 0. And that's what it means to have phase cancellation. It's a mathematical situation in which no sound is produced because it literally cancels out. Now we can look here again. If I decided that I still wanted the sound to play and I just wanted to have less phase cancellation, because keep in mind that phase cancellation that is totally canceled happens when the signals are completely out of phase. That's what that means. When they're totally reversed to the point that the exact same signal is duplicated and the low point matches up with the high point exactly in time, that's being completely out of phase. They're 100% different, like opposite. But if I play the sound again, so you can see that they're both playing, and I reduce the amount of one of them, some will start to come back. So what you're seeing here is partial phase cancellation, where it's not completely out of phase, but when it's added together, the presence of number 2, this copy, reduces the amplitude of number 1 because since they're not perfectly aligned, but they're exactly the same, this one is acting as a negative. So to understand this is very simple, right? If you have 1 and you say 1 plus 1 would be 2 because you made a copy of the one thing you had. But you said, I'm not going to use an entire 1. I'm going to just take half, and then you made that half negative. You would say, before it was negative, you would say 1 plus 1/2 equals 1.5. So if it was just like this, then I could turn it down and it would just turn down. And if I was to just turn it up, the volume would turn up because they're the same. But when this one is negative and they're equal, it becomes 0. So logically speaking and mathematically speaking, if it was less, say it was 1/2, and let's say that that's about 1/2, you would still have half left. And that's the same way phase cancellation works. If you have 1 and you have -1, which means an inverted copy of the sound or the signal, then you have 0. But if you have the signal and then you have a copy of it, but it's not as loud, which in this case we will refer to as -1/2, that's like 1 minus 1/2 because it's 1 plus -1/2. So what I'm saying here is that you can use phase cancellation musically, and to be honest with you, I have never done it, but there are instances where people do. And I think there are plugins that do, and I think that's honestly the idea behind a phaser, even though I think that might be something with developer software. I'm not exactly sure. I do believe, though, it makes two copies of the signal and it causes a phase misalignment that's not 100% phase cancel so that it will produce a change in the timbre of the sound. That's what I believe happens if I remember correctly. But it is used. That's the point. And even if I was to modulate this right here with an LFO, and I said I want the phase to be aligned or misaligned over time like that, you can see on the oscillator that the nature of the sound would change. So that sort of gives credence to what I believe happens. I have to look that up for whenever I do a video about phasers, but just keep that in mind. I'm pretty sure they use an LFO to modulate the phase of one signal that's a copy of the other signal to change the timbre of the combined total. In the same way that you wouldn't completely cancel this out because this is a positive one plus a negative one. But if I reduce the amplitude of the negative one, then it's like a positive one plus a negative 0.6, for example. And so that's the nature of phase cancellation. And it's important to understand it fundamentally to understand monocompatibility. So to summarize, or one more time, if you have one signal, you copy the signal, you reverse the polarity, you combine it at the same amplitude or volume to the original, they will cancel out because the highest point meets the lowest point between the original and its duplicate. And if you consider the highest point to be 1 and the lowest point to be -1, when you add them together, they make 0. So that's phase cancellation. And I'm not going to include any audio in this video. It's already late. And I still got to do the rest of the editing, take out mistakes and stuff like that. It should actually be going up right now while I'm recording it, but it was difficult to pick a topic. So, with that, I thank you for watching, and I hope you have an awesome day. Peace.